After Professor Anupam Garg's beautiful talk yesterday, I feel quite apprehensive about speaking on a related subject. I also see that young people, students nowadays are really precocious compared to my generation. But let me hope there are at least some young people here to whom some of these ideas may be new. So the idea of Wigner distributions is almost as old as quantum mechanics itself, almost. So I would like to describe a new approach worked out by Professor Subhash Chaturvedi, myself, and a few others in the familiar case of continuous variables, and then see if that method can be extended to systems with a finite dimensional state space. And along the way, I will recall a few important historical steps. So for a one Cartesian degree of freedom, quantum mechanics, we have basic, is it on? Yeah. We have basic position and momentum operators, Q and P, obeying the standard canonical commutation relations. Q commutated with P is IH bar, and the other two are 0. I depart from Professor Garg's notation. For me, carets are operators. Okay? Just bear with me for just a little while. Now, these operators, as we know, they act on an infinite dimensional Hilbert space, and we can denote vectors in the space by ket vectors, psi, phi, and so on. And because this is a Cartesian pair, each of these two operators, Q and P, has all real numbers as ideal eigenvectors and eigenvalues, and they are subject to the usual Dirac delta function normalization, orthonormalization. So this is the momentum eigenfunction and eigenvalues equation, and the overlap is the familiar plane wave. Now, as everybody knows, there is no intrinsic rule to pass from classical dynamical variables, functions of classical Q and P, real Q and P, to corresponding quantum mechanical operators acting on that Hilbert space in any way. There is no canonical or preferred rule, intrinsic rule. The Weil rule given in 1927 in a couple of lines in his book is a convention or a proposal, and it says the passage from classical functions on two-dimensional phase space to operators on the Hilbert space is to be based on this mapping. This classical function is mapped into that unitary operator, lambda and mu being real, and then you use Fourier transformation and linearity. In that way, you find that the Weil rule leads to this result. To each real classical phase space function, it associates a definite Hermitian operator, F with a roof on it. Now, all this is simple-minded physicist way of doing these things. I don't aim at any kind of rigor. A few years later, in 1932, Wigner found a way to represent density matrices or states in quantum mechanics by real distributions on the classical phase space of real variables Q and P. And these are the expressions he gave in 1932. The Wigner function for a pure state with wave function psi is obtained in this way. You split the arguments of psi and psi star by Q prime and take the Fourier transformation with respect to Q prime. If you have a general state with a density matrix rho, you use the Q space matrix elements of rho in this manner. So this was found by him in 1932, and somewhere or other he writes or says that there were many possible ways of defining such a classical looking representative of a quantum state, and this looked like a nice one. During the 1940s, the work of Groenewold in the Netherlands and Moyal in England clarified the situation, the relationship between these two ideas and the major properties of this mapping. So let me just show you what the result of this analysis was. Here are the main properties characterizing this pair of ideas: the Weil rule to go from classical functions to quantum operators, the Wigner rule to represent a quantum state by a classical function on phase space. Both of those are based really on the same principle or rule, so I would just combine them in this way. General classical functions, real, for example, would correspond to Hermitian operators by the Weil prescription. For density matrices, for convenience or convention, another numerical factor is included, and so density operator rho is represented by its Wigner function, the same rule of association. And if you use this for states and operators in quantum mechanics, you get this traciality condition. The trace of the product of the state rho and the observable f is a classical looking phase space average. I would like to mention in passing, this is probably well known to many, that a very useful role is played in this machinery by the parity operator. If there are any questions later, I will explain how that, indicate how that happens. The remaining important properties are these. The Wigner function is pointwise real on the classical phase space. And there is a beautiful theorem of Hudson from not very long ago, by that I mean 1974, which says that if a Wigner function in this Cartesian situation is non-negative, it can happen only if the wave function or the density matrix is a Gaussian. Any non-Gaussian psi or rho definitely leads to W, which becomes negative somewhere. Then there is this very interesting bound on the magnitude of the Wigner function at every point in phase space. Mod W is less than or equal to 1 by pi h bar, and there is an overall normalization condition corresponding to trace rho equal to 1. There are some, so as we see, for generic states, W will become negative somewhere, but there are some important restrictions how negative it can become. The basic marginal conditions are that if you integrate over P, you get the position probability density. If you integrate over Q, you get the momentum probability density. More generally, there is marginal type relation. If you integrate the Wigner function along a line at some angle to the Q axis, let us say, the result is again a real probability density, which is written sometimes in this way. And this is used in quantum tomography. And this traciality, I repeat, the rules of correspondence for general operators or observables and for density matrices differ by a numerical factor, and so you get these relations. So these are called the traciality relations. Now, during the 1940s, there were quite a few letters exchanged between Dirac and Moyal. Moyal at that time was in the United Kingdom. However, Dirac was not encouraging at all. It took some time for the ideas to mature and to be understood properly. And I might read one or two sentences from replies that Dirac made to letters from Moyal. In one letter of March 1945, Dirac says, "I have rather forgotten the details of your work and would be glad if you let me see again the part of it dealing with f of qpt, I may get a more favorable opinion of it this time. That is one statement. Another one. Dirac criticizes some of the arguments of Moyal and then says, my distribution is not a real number in general, so it is worse than yours, which is real but not always positive. But mine is connected with a general theory of functions of non-commuting observables. And then he says that he is writing up his work for publication and he would like to refer to Moyal's work, and he asks Moyal, may I refer to your work in such and such a way? So it was so polite and kind, but not encouraging. And one last similar, in the same vein, I will read it to you. Last one. This is in just about May 1945. I still do not agree that your function gives correctly the average values of all Hermitian operators considered in classical mechanics. I don't know why he wrote that. It is true that, etc., etc. So I just want you to be aware, Moyal later in his life settled in Australia after having traveled in many countries of the world. And his wife wrote a biography of Moyal and give a nice account of his work. And in that biography, in the appendix, is the Dirac-Moyal correspondence. These letters are in the Bassar Library of the Australian Academy of Science in Canberra. Okay. So it's a nice biography to read as well. Okay. So one useful idea of Dirac from this period is what we would like to explore and exploit. This is a paper he wrote in 1945 in the Reviews of Modern Physics, and it was to celebrate Niels Bohr's 60th birthday. And this is what the title was, On the Analogy Between Classical and Quantum Mechanics. And it is in this paper that he gave an outline of a general theory of functions of non-commuting variables. This is what he refers to in his letters to Moyal. So I would like to show you how we have tried to use Dirac's ideas in this 1945 paper to understand the Weil-Wigner phase-space description of quantum mechanics from a different point of view. It is quite elementary. It is a two-step process based on the Dirac idea, and each step is quite elementary, as you will see. So the first step is the following. This is extremely easy. This is Dirac's idea. Take any operator on a quantum mechanical Hilbert space for such variables Q and P. You can immediately associate with it a C number, in general complex function on the classical phase space. So from the operator A caret, I go to a classical function A1 of QP, which is the matrix element of A between a position eigenstate on the left and a momentum eigenstate on the right, along with the plane wave phase factor. So this is the expression. So this is the idea of Dirac, that operators of quantum mechanics can be described not just in the usual matrix sense, but by what he calls mixed matrix elements. So this is step one. It is so trivial. It is such a simple rule to represent or describe any quantum mechanical operator by a corresponding classical function on phase space. There is no statement that if A is Hermitian, the result will be real. Not at all. In general, A1 will be complex even if the operator is Hermitian. Having made this, and it is very important in this context that this plane wave factor is always non-vanishing. That plays a key role in the arguments. Now it is very trivial to see that the trace of the product of two operators can be written as a fourfold integral, two phase space integrations, the product of the function representing operator A and the function representing operator B with a kernel in between, capital K, which depends on one phase space point, the argument of A1, and another point, the argument of B1. And here is the expression. This is extremely simple algebra. I just would like to mention the exponent here can be interpreted as a geometric phase, and we have translation invariance in the phase space and symmetry under interchange of these two phase space points. So this is step one. I repeat, it is the Dirac idea of describing operators by classical C-number functions, and the appearance of classical phase space is trivial, no effort at all. The next step is the one which is a little bit non-trivial. Is there a way to somehow remove the kernel K which appears in the trace formula? Suppose you are able to write capital K in such a form in terms of something simpler than K. I denote it by psi, and I have written it here. This is the origin of the idea square root method, square root procedure. Suppose you are able to find a function psi of 2 points in phase space such that K can be written in this form, then we can do the following. We go to that trace formula, put this expression for K in there, attach one factor of psi to one of the two functions, attach the other psi to the other function, and then in a sense you are home. You can say the trace of two quantum mechanical operators is a phase space classical integral of two C-number functions, and here are how A and B of QP classical functions are obtained from the first set A1, B1 by putting one psi with A1, the other attaching it to B1. Okay. So if you can do this, if you can construct some square root kernel psi, this is what you can achieve. Now in the Cartesian continuous case, using the fact that all the variables we are dealing with are continuous variables, they run from minus to plus infinity, and if you choose this square root quantity psi to be also translation invariant and symmetric on its own, then there is a very simple and natural solution. Okay. Point-wise, it looks like the square of K, but kernel-wise, it is a square root of K. Okay. Just a small distinction. If you now use this, put this result back here, you get back completely the Weil-Wigner situation. Weil's rule, Wigner's rule, trace reality, everything comes through. Okay? So this is all that I want to tell you about the Wigner Dirac idea. The introduction of a classical phase space description is trivial. The only remaining work is to extract the square root of a simple looking kernel, and it turns out in the continuous variable case that is also very easy. Not much effort is involved. Now I go on. So the question we asked ourselves is the following. Can we approach the problem of Wigner distributions for finite state quantum systems in a similar way? There is some very good early work by Wouters, but I don't have time to go into it. I just mention it. So let us see what you do in the finite dimensional case. For an n-level quantum system, n greater than or equal to 2, we have a Hilbert space of dimension capital N, and we introduce in the pattern of the Cartesian case discrete position and momentum variables Q and P, which are integers from 0 up to n minus 1. And in all addition and multiplication, whenever relevant, it is always modulo n. Then you introduce in this Hilbert space two orthonormal bases, a position eigenstates basis, momentum eigenstates basis, but these are strictly normalized to unity, each one of them. They are all unit vectors, and here is the overlap, the analog of the plane wave. Now, clearly, any operator on Hn can be described in the standard way by a matrix in the position coordinate description or a matrix in the momentum space, and in either case, the product of operators corresponds to matrix product. Now we use the Dirac idea. Can we describe an operator A by an array? Let us not call it a matrix. The array A1 corresponding to the operator A roof is the same prescription as in the Cartesian case. A mixed matrix element of the operator times a plane wave factor. Here it is. So question is, can we work with this kind of description? Then you can carry out the trace operation. Instead of phase space integrals, you have summations over phase space, and the trace operation involves naturally the function A1, the function B1, and a kernel K standing in between. Now I introduce a little bit of a notation. The classical phase space in this problem, I denote it by gamma 0. It is a square grid. It's a collection of n squared points with q and p running from 0 to n minus 1. Given any 2 points on this phase space, we can define a symplectic inner product, and here it is. The symplectic inner product of qp with q prime p prime is this antisymmetric combination modulo n, and we can also introduce an n squared dimensional Hilbert space, script k, which is the set of all square summable functions on the phase space. Now, the properties of the kernel appearing in the trace are very simple in the discrete case as in the continuous case. There is symmetry, there is translation invariance, and the thing is essentially unitary. Except for a scale factor n squared, it is unitary. To go further, it is useful to think of this phase space gamma 0 as an abelian group of order n squared. By abelian, I mean here pointwise addition of components. Q and q prime get added, p and p prime get added, always modulo n. So being an abelian group, it has n squared one-dimensional unitary irreducible representations. They are called characters, and the representations themselves can be labeled by points of gamma 0. So for each point sigma prime in the classical discrete phase space, you have one irreducible representation of this group, and here it is. And they are orthogonal, there is a normalization factor, and so on. So the characters of gamma 0, thought of as an abelian group, form an orthonormal basis for that script K Hilbert space. It also turns out that our kernel K, which we are interested in, has these characters as its eigenfunctions or eigenvectors, and here are the eigenvalues. Every eigenvalue is n, a scale factor, times a phase factor. So now the question is, can we decompose the kernel which appears in the trace formula again in terms of something more elementary, in terms of a simpler expression psi of 2 points on phase space. Writing it in this way makes it clear that the symmetry of capital K is automatically achieved. But written as a matrix relation, it reads psi is K is psi transpose times psi. Then with any such psi, obeying this relation, you have a way to propose a Wigner type description of operators while Wigner type description. You take the previous description, the Dirac prescription, attach xi to it and call it A. Take B1, attach xi to it, call it B, and the trace looks so simple. So this would be, for any allowed choice of xi, a possible way to describe the while Wigner machinery for a finite state system. The matrix A on the Hilbert space would correspond one-to-one to a classical function of discrete coordinate and momentum. Okay, this is the idea. Now, so does this work in the discrete case? Yeah. So I make now, as we had in the Cartesian continuous case, let us suppose psi is symmetric. Then kernel K is exactly the square of psi. So the psi you are looking for is some square root of capital K as a kernel. Now we know all the eigenfunctions and eigenvalues of K. So the most general solution of this equation, the most general square root of K, can be easily written down, and I have the entire expression here. At each point of phase, there is a summation over phase space point sigma double, and at each point of that phase space in this summation, there is an undetermined sign, +1 or -1. One free sign factor for each character of gamma 0 as an abelian group. So this is the most general solution to this problem. So then the question is, can we somehow get restrictions on these signs, determine them or limit them in some way? If you demand the standard marginal probabilities should be reproduced by this machinery, that is, if you sum over momentum alone, you should get a position matrix diagonal elements of the density matrix. If you sum over position, you should get momentum. This pair of conditions fixes some of these free sign factors. S of Q0 should all be 1 for all Q. S of 0P should also be 1 for all P. Now the question is, can we generate more such restrictions on the signs, because many signs are undetermined at this stage. So the idea of further marginals is similar to what I showed you in the continuous case, integrating the Wigner function along a line tilted in the phase space plane. So for this, we have to use the idea of isotropic lines in this discrete phase space. An isotropic line is a maximal set of n distinct points, including the origin in the phase space, and with this property, any 2 points on this line should obey this condition, that is that the symplectic scalar product of those 2 points should be 0 modulo n. So one can ask, can one determine all possible isotropic lines, and then for each line, can one impose a condition on the marginal? The sum over the Wigner function along an isotropic line should be a probability distribution. Suppose you do this, imposing further marginal conditions using each isotropic line. Here are the results, a little bit of algebra. For the odd dimensional Hilbert spaces, there is a unique solution. Everything can be satisfied, all the marginals can be satisfied, and the sign factors are determined at every point of the phase space. S of sigma is -1 to the power QP. If either P is 0 or Q is 0, that gives you +1. In the case of even dimensions, the situation is very different. The set of all isotropic lines can be described and written down. It is a little bit intricate. But from our point of view, if you were to impose marginal conditions for all isotropic lines, in the even case there are inconsistencies. So you cannot use such an approach. You have to choose some maximal set of isotropic lines and impose conditions only along them. increasing that set of lines, conditions, leads to algebraic inconsistencies. So you choose some maximal subset, write down those marginal conditions, then it turns out some more of the signs are determined, but some remain free, a fairly large number. So in summary, for the odd dimensional case, the situation is very simple. There's a unique, essentially unique way to choose these sign factors, therefore a unique prescription to define the Wigner distribution, to define the Weil rule, and so on. For even dimensions, there are many, many solutions which grow quite a bit, quite rapidly as the dimension increases. Incidentally, the unique solution in the odd case corresponds exactly to the use of parity in this situation, and that is something good. For the description and analysis of isotropic lines, one can use a discrete version of the symplectic group. It plays a role, but it is a little bit harder to deal with than the continuous case. So this approach does then lead to a unique definition of Wigner distributions for odd dimensions. It leads to many possibilities in the even case. Now I come to another square root idea in the odd dimension case, odd dimensions only. This is based on a very nice group theoretical result. The result is that if capital G is a finite group of odd order, every element of the group has a unique square root element. This is something which is probably not that well known. I learned it from Chaturvedi while working on this problem, but this is not true for groups of even order. For example, it is not true for any permutation group, because permutation groups are all of even order. If I am given an odd capital N and the corresponding Hilbert space, of course one choice is to take G to be the cyclic group of that order. That would certainly be a finite group. But it turns out that non-abelian choices are also available. And some of the smallest odd n for which there is a finite group of that order and which is non-abelian is n equal to 21. Okay. Then the next is at n equal to 27, then 39, and so on. So in any case, what we do is the following. We let the role of position in the previous description be played by elements of our group. So there is one ket vector G for each group element. They are orthonormal, and you can imagine that for the identity element, the vector has some special status. Then you ask about the unitary irreducible representations of G. I denote them in the usual way suggested by quantum theory of angular momentum. So I label the representations by J, let the dimensions be Nj, and here are the rows and columns, and this is a well-known result of group representation theory. The sum of the squares of the irreducible representations is the order of the group. So while position is, the role of position is played by group elements, the role of momentum is played by these matrix elements, and here is the expression. So this is the analog in this approach of the overlap between a momentum eigenstate and a position eigenstate. So this is the analog of the plane wave factor. Okay. Then given this machinery, this much machinery, here is a possible definition of a Wigner function for a density matrix corresponding to any state psi. I have written it here. There is an error. There should have been a psi here. It is missing because this PowerPoint presentation, I don't know how to make them. My colleague Arvind did them. So we used classical communication and non-local operations, and this error came in. All right. But it has all the nice properties you would like. The analog of reality for the Wigner function is here. The marginals for position probabilities is here. This is the marginals property for momentum, suitably generalized, and this is the traciality condition. So all these ideas are there. And I just want to mention in passing that soon after this paper was published, I think it was in Pramana, there was a paper from a group in Vienna, and I remember one lady author's name, Heidi Narnhofer, and I had never heard her name before. It turned out she was a student or associate of Walter Thirring. And this was a paper which is somewhat mathematical, but Simon told us she has referred to our Pramana paper in her paper 14 times. This must be a record from a Pramana paper. So then I immediately imagined, oh, she has referred to it so often, it must be very easy to understand. I couldn't understand a word of it. So that was a great disappointment, but there it is. I think Subhash also knows that paper. It was very hard for us to understand. So this is what we have done, and this stream of ideas, we are still trying to pursue it, because you see in the even dimensional case, we do not have a nice, satisfying resolution of the problem. So I will end, I am in time. It is nice that the most, well, we all know the most famous use of the square root idea in physics, I think, is in connection with the Dirac equation. So it seems appropriate that echoes of that square root idea can be used in the case of Dirac's brother-in-law's distribution. So I will stop at this point, try to answer any questions, and Professor Chaturvedi's presentation, which follows immediately, will describe our later and ongoing work. Thank you very much.
Got any questions?
That's just for my curiosity.
Yeah.
This you mentioned about the Berry phase connection in the beginning. So in the case of the Wigner function and the group thing, have you noticed the Berry phase connection in
No,
a...
I didn't.
Okay.
I did not. The right person is Swami Samuel here. We should talk to him. We should ask him,
Okay.
because that would be in a discrete case. What I noticed was in the continuous case.
Okay.
Yeah.
No, I just
Yeah.
wanted to comment that in your early transparencies,
Yeah.
when you associate a function to an operator,
Yeah.
it's what some of the people in the audience would call a weak value.
A what?
A weak value.
I see.
That's what it looked like. If you look at the first or second transparency, yeah.
The continuous case.
Right, yes, right
Yeah,
here.
this one,
That
yeah.
A1,
Yeah, yeah.
because QP never vanishes, you can put it in the denominator.
Yeah, that is very important. Yeah, I'm glad you pointed it out. I had not realized the connection to current ideas, but I do remember Dirac making this point that whatever he wanted to do, he could do, because this is always non-vanishing. That is very important. Yeah.
Thanks. Maybe I could just make a comment on this point. Unless I'm mistaken, this is exactly the idea that Jeff Lundin implemented experimentally to do the weak value tomography.
I see.
Okay.
I don't know.
Oh, you didn't know that? Okay,
didn't,
but yes.
yeah.
But exactly by measuring elements like that as a weak value and using the fact that it is a representation of the state. Yeah.
Thank you very much. Swamiji and I can start talking again together. Thank you very much. Oh, yes.
So this finite Hilbert space thing that you do with modular addition, this is very reminiscent of what we do in solid state physics with the von Karman boundary conditions, and
Yeah.
you know, in the natural system it suggests is motion on a lattice.
Okay.
And so I don't know, does it, have you thought about whether it's another way or a better way of thinking about semi-classical dynamics for
No.
for that kind of physical problem?
No, at the moment, our target is the following. In odd dimensions, everything is so beautiful, so unique, and the role of parity comes out very well. In even dimensions, there are solutions, but there are many solutions. And the first target for us is to see, is there a natural way to pick one of the possible solutions in even dimensions? If we succeed, then I will go in the direction of weak measurement, I will go in the direction of many body physics, many directions after this is done. Until this is done, you cannot sleep. Okay.
Great, thanks very much. Let's thank the speaker
Take this
again.
away.